if we have a vector field F and we have a curve going from point A to point B, so let's call this C, then we've seen that in general, the line integral over C f dot dr, this depends on C and not just on A and B. So meaning if we took some different curve, so we called this like C prime, then in general, so same endpoints, but a different curve, in general, these two will be different. So it might be surprising, though, that often, so maybe I should say first, many of the vector fields F, which arise in practice, this is not the case. So a definition, so you will, for a lot of F, you will always get the same answer. So definition, so if F is a vector field on defined on an open region D, then we say that F is conservative if for every pair of points A, B, and D, we have, so integral C1 f dot dr equals integral over C2 f dot dr, where C1 and C2 are any curves connecting, so from A to B and lying entirely in D. And so in this case, we often write just integral A to B f dr, since this will only depend on the points A and B, to emphasize this path independence. The term conservative comes from physics, where it refers to, so this is related to conservation laws, like conservation of energy. And so for example, gravitational fields G and electrical fields E are conservative. So this is why I said what I meant by these arise often in practice, they arise in physical situations. So a gravitational field is one describing the force of gravity. So the force exerted on a mass m by a gravitational field G is F equals mg, and the force exerted by an electrical field on a charge Q is given by F equals QE. So mathematically, these are the same, but they have sort of different physical units. And so the fact that these are conservative translates to saying that the work needed or done by, I should say, the work done by a gravitational or electric respectively electric field in moving a mass, respectively a charge, from point A to point B doesn't depend on how you get on how you move from point A to point B. So it doesn't depend on the path taken. Only depends on the endpoints, which might be surprising. Okay, so we'll show under very mild conditions that are always satisfied in practice that F, a vector field F, is conservative if and only if it arises as a gradient vector field. And so in this case, the little function f is called a potential function. So this is, in a way, this is a sort of like a vector antiderivative of big F. So a potential function is another term coming from physics. So, for instance, we have a gravitational potential is a thing whose gradient is a gravitational field, and similarly, an electric potential is a thing whose gradient is an electric field. And so, just as this is sort of a form of an integral, of an indefinite integral, there's a version of the fundamental theorem of calculus we'll discuss. So, fundamental theorem of calculus is that integral from a to b of f dr, so when f is conservative, that this is f of b minus f of a. So, for example, if we let f x, y, z equals negative 1 over x squared plus y squared plus z squared, we could ask to find the work done by the gradient of f in moving from 1, 0, 0, let's say, to negative 2, 0, 0, via any point. So this isn't defined. F is not defined at the origin. So our path from here to here is going to have to go some path other than a straight line, but the answer won't matter. So via any path that's not passing through the origin. Well, so integral 1, 0, 0 to negative 2, 0, 0 f dot dr by this sort of fundamental theorem of calculus is just negative 1 over x squared plus y squared plus z squared, negative 2, 0, 0, 1, 0, 0. So that's 1 over 4 no, negative 1 over 4 plus 1 is 3 over 4. And this potential function here, this is sort of an inverse square law. So this is like a physically realistic way to model the effects of gravity or of temperature and so on. So usually, I mean, up to a constant, so maybe you would put negative mass 1 over mass over x squared plus y squared plus z squared here. But that can sort of, the constant, up to a constant, this is sort of that potential function.